Introduction to adiabatic changes. An adiabatic process is one in which no heat transfer takes place between a system and its surroundings. In this lesson, you will be able to understand the adiabatic process of a gas, adiabatic expansion, adiabatic compression. Use the equations P, V to the power gamma is a constant, T, V to the power gamma minus 1 is a constant for adiabatic changes. Illustrate the PV graph for an adiabatic change and use the first law of thermodynamics to explain changes during an adiabatic process. Click on the forefinger. The vapor released from an aerosol can undergoes an adiabatic expansion. No energy is supplied to the vapor for it to do work during expansion. The energy comes from the internal energy of the vapor. From the first law of thermodynamics, delta Q equals delta U plus W. Since no heat is supplied to the vapor, delta Q equals 0. Hence, delta U equals negative W. This means that the internal energy of the vapor decreases and the temperature of the vapor decreases. To illustrate an idealized adiabatic expansion of a gas, a well-insulated cylinder is used as shown. Click Remove to allow the gas to expand adiabatically. When the gas expands, work is done by the gas. Since no heat enters the gas, the internal energy of the gas decreases. The final temperature of the gas T2 is less than its initial temperature T1. What happens to the pressure of the gas during an adiabatic expansion? Answer: the pressure decreases. A piece of paper is in a cylinder which has thick insulated walls. Click Add and observe what happens to the piece of paper when the piston is pushed into the cylinder. Why does the paper burst into flame? Answer: when the piston is pushed down fast, work is done on the gas. Since the walls of the cylinder are insulated, no heat escapes from the gas. The temperature of the gas rises and the paper is ignited. To illustrate an idealized adiabatic compression of a gas, a well-insulated cylinder is used as shown. Click Add to compress the gas adiabatically. When the piston is pushed down fast, the gas is compressed adiabatically. What happens to the pressure and temperature of the gas? Answer: the pressure of the gas increases and its temperature increases. This principle is used in the diesel engine to ignite the diesel-air mixture. Summary: in an adiabatic process, no heat enters or leaves the gas. Applying the first law of thermodynamics, delta Q equals delta U plus W for an adiabatic expansion. Delta Q equals 0. Hence, delta U equals negative W. Energy required for the gas to do work during an adiabatic expansion comes from the internal energy of the gas. An adiabatic expansion results in a decrease in pressure and temperature. When a gas is compressed adiabatically, pressure of the gas increases, work is done on the gas, the temperature of the gas increases. In a diesel engine, the diesel-air mixture is compressed adiabatically. Its temperature rises and the mixture is ignited. A gas undergoing an adiabatic change obeys the following equations. P v to the power gamma equals constant and T v to the power gamma minus 1 equals constant, where P is the gas pressure, V is the gas volume, T is the absolute temperature of the gas, and gamma equals CPM over CVM, the ratio of molar heat capacities of the gas. Based on these equations, we have 1. P1 V1 to the power gamma equals P2 V2 to the power gamma. T1 V1 to the power gamma minus 1 equals T2 V2 to the power gamma minus 1. 1.25 mole of a gas at a volume of 2.81 times 10 to the power negative 2 meter cube is compressed adiabatically from a pressure of 1.0 atmosphere to 5.0 atmospheres. If the new volume of the gas is 8.9 times 10 to the power negative 3 meter cube, calculate the value of gamma, the ratio of the molar heat capacities of the gas. Hence, deduce the nature of the gas molecules. Given 1 atmosphere equals 1.01 times 10 to the power 5 pascals. Select the correct formula from the list and drag and drop the appropriate values into the equation. A diatomic gas is expanded adiabatically from a volume of 1.45 times 10 to the power negative 4 meter cube at a temperature of 447 degrees Celsius to a final volume of 3.0 times 10 to the power negative 4 meter cube. Calculate the final temperature. Select the correct formula from the list and drag and drop the appropriate values into the equation. Summary. The equations used in the adiabatic changes are P v to the power gamma equals constant, P1 v1 to the power gamma equals P2 v2 to the power gamma, and T v to the power gamma minus 1 equals constant, T1 v1 to the power gamma minus 1 equals T2 v2 to the power gamma minus 1, where P is the gas pressure, V is the gas volume, T is the absolute temperature of the gas, and gamma represents CPM over CVM, the ratio of the molar heat capacities for the gas. In an adiabatic expansion of an ideal gas, the equation PV equals nRT applies. The volume V increases as the gas expands. Both the temperature T and the pressure P of the gas decrease. The temperature decreases because the internal energy of the gas decreases. Drag the marker from point A to point B and observe the changes to the gas. From the first law of thermodynamics, Q equals delta U plus W. For adiabatic changes, Q equals 0, therefore 0 equals delta U plus W. Hence, W equals negative delta U. When the gas expands from a volume of VA to VB, work is done by the gas. Its internal energy decreases. The temperature of the gas decreases from T1 to T2. For an ideal gas, when an isotherm and an adiabatic pass through the same point on a PV diagram, the adiabatic is always steeper. Now, drag the marker back from point B to point A. During an adiabatic compression, the temperature of the gas rises. Summary. During an adiabatic expansion, the pressure of the gas decreases. Work is done by the gas. The internal energy of the gas decreases. The temperature of the gas decreases. During an adiabatic compression, the pressure of the gas increases. Work is done onto the gas. The internal energy of the gas increases. The temperature of the gas increases. For an ideal gas, when an isotherm and an adiabatic pass through the same point on a PV diagram, the adiabatic is always steeper. Drag the marker from the point A to the point B and observe the area under the PV graph that represents the work done by the gas during an adiabatic expansion. The work done during an adiabatic process can be expressed in terms of the change in the internal energy of the gas. Click Step 1. If n moles of an ideal gas undergoes an adiabatic process and its temperature changes from T1 to T2, the change in its internal energy, delta U, can be expressed in terms of its molar heat capacity at constant volume CVM. Click Step 2 and Step 3. Derivation of the expression for work done during an adiabatic expansion. Consider a fixed mass of a gas at an initial pressure of P1, volume V1 and temperature T1. When the gas expands adiabatically to a volume V2, its pressure changes to P2 and its temperature drops to T2. Summary. Area under the PV graph of an adiabatic process for an ideal gas represents the work done. Work done W equals negative delta U equals N times CVM of T2 minus T1. Expression for work done is W equals 1 over gamma minus 1 times P1 V1 minus P2 V2. W equals NR over gamma minus 1 times T1 minus T2.